this video we will see an example of a break-even point calculation. Break-even point is a business activity level at which the total revenues of an organization will cover its total costs. The importance of break-even point stems from the fact that beyond this business activity level, the organization will start to become profitable, to make money. So it is important for the businesses to understand at which point they will reach profitability. For the break-even point, we have the formula that we can see in the slide. So the same notation that we're familiar with. So FC is the fixed cost, VC is the variable cost per unit of output or business activity, and then here we have a new parameter, which is the revenue per unit of output or business activity, which is denoted by R here. Let's see the example. The example is about a company that provides online auction services. They have 3 different alternatives for their capacities based on the number of servers. So a 10 server, 20 server, and 30 server alternative. And for each alternative, as we can see in this table, there is a fixed cost and there is a variable cost. And the revenue per unit of output is 0.5, as you can see in the table. So here for each alternative we can see another column which determines the maximum output. So this is an important aspect of this example that we need to take into account. I will tell you when and how it will affect our calculations. And then we have 3 different scenarios for demand. 15 millions, 30 millions, and 45 millions. And there is a probability associated with each demand scenario. We have to answer to a number of questions. In the first question, we need to calculate the break-even point for each capacity alternative. Of course, we will use the same formula we saw in the previous slide, and then we will get these numbers. But let's see how these numbers are calculated. For example, let's see how the break-even point for the second scenario is calculated. For the second scenario with 20 servers, the fixed cost is equal to 19,000. And we have a variable cost equal to 0.003, and the revenue per unit of product is, or per unit of output is 0.5. And if we substitute these numbers into the formula that we have here, we will get 181 and 86, 181,086.5. Let's round it up, so we'll get 87. So it is the number that we can see in this table. In a similar way, we can calculate the break-even points for the other 2 alternatives. What does this number says? It says that for the first scenario, for example, we need a business activity level more than 101,000 in order to be profitable. After that point, we will start to make money. But if we have a business activity level less than this 101,000, then our total revenues will not cover our total costs, or in other words, our costs will be higher than our revenue. In the second part of the example, we want to determine at what demand level would the organization be indifferent between having either the first alternative or the second alternative. To answer this question, we need to equate the total cost functions of the first and second scenario alternatives. So here on the left hand side of this equation we have the total cost of the first alternative, and on the right hand side we have the total cost of the second alternative. So we substitute the numbers and then solve for x, and then we get x equal to 20 millions. We can also plot these, let's say, total cost functions as a function of the business activity level, and we'll get this figure. Here we can see 3 lines for 3 alternatives that we have, and the indifference point is a point at which the total costs of the 2 scenarios or a pair of scenarios, let's say alternatives, will be equal to each other. For example, this 20 millions that we calculated is in fact the point that the total cost line for the first scenario, first alternative, and the total cost line for the second alternative will cross each other. In a similar way, we can calculate the indifference points for the other 2 pairs of alternatives. Let's say, let's look at this from another point of view. In fact, when we want to calculate the indifference point, we want to calculate a point at which the profitability of the organization from 2 different alternatives is equal to each other. On the left-hand side of this equation, you can see the total profit of the organization if it uses or if it chooses the first alternative. So we have FC1 and VC1 to denote the fixed cost and variable cost of the first alternative, respectively. And then on the right-hand side, these numbers should be 2, so I will fix it now. Okay. Okay. And on the right hand side we have the total profit of the organization if it chooses the second alternative. And here FC2 and VC2 are denoting the fixed cost and variable cost of the second alternative, respectively. If we cancel this first expressions, revenue per unit, or this is R multiplied by X, from both sides and then multiply both sides by -1, then we will get this equation, which is in fact the equation that we saw in the previous slide. And then if we solve it for X, if we solve this equation for X, we will get this formula. And this is the formula for the indifference point for 2 alternatives, 1 and 2. We can, for each pair of alternatives, we can calculate the indifference points, and these are the numbers that we will get. In the last part of the example, we need to calculate the expected value for each capacity alternative. And here we are doing the calculations for the first alternative with 10 servers. Similar to the previous example, we need the fixed cost and variable cost of the first alternative, and also we need to know about the demands in each demand scenario and of course the associated probability. Let's see the calculations. So the profit, this is denoted by P, associated with the first demand scenario, which is 15 millions, is equal to, first we have revenue, which is 15 million multiplied by 0.5, which is the unit revenue, minus the total costs. So the total cost for the first scenario, we have a fixed cost equal to 50,000, and then plus the variable cost, and in this demand scenario the X, or the business activity level, is 15 millions multiplied by the variable cost that you can see here to 0.005, and then it will give us this number. Let's move to the next demand scenario, the second demand scenario with a demand equal to 30 millions. Here, to calculate the revenue, we will multiply 0.5, which is the unit revenue, by 20 millions. But why 20 millions? If you remember, we had a maximum output limitation for each demand alternative. For the first demand alternative, the maximum output can be 20 millions, as you can see in this table. So we cannot provide more than this. So this is the limitation that we have. So even though the demand is 30 millions, we will at most sell 20 millions. So that is why in the revenue function we have 20 millions multiplied by 0.5, which is the unit revenue. So this is the revenue minus the total costs, again fixed cost plus unit variable cost multiplied by, again here we have the limitations. Even though the demand is higher, but we can only satisfy 20 millions of this demand, so we are using 20 million here. So we'll get this number as the total profit. The calculations are similar for the last demand scenario, and then for the expected value, or here the expected profit, we need to multiply the profit from each demand scenario by its probability and then sum over different scenarios. So for the 10 servers, this is the profit from the first scenario multiplied by its probability, profit from the second scenario multiplied by its probability, and then the same for the third scenario. So we'll get a total expected profit equal to this number that you can see. So if we do the same calculations for the other capacity alternatives, we'll get these results. And based on these results, we can say that the third alternative has the highest expected value or the highest expected profit.